Hi, everybody. Welcome back to Climate Solutions. And today we're going to build on what we did last time. So in the last module, we talked a little bit about planetary energy balance and how we can think about the things that control climate, greenhouse gases in the atmosphere, the reflectivity of the Earth's surface. But today we're going to talk about climate models and how we use them to understand both how the atmosphere is changing now and why the atmosphere is changing now and why the climate is changing now, but also how we use them to think about what our future might look like. Now, this is obviously a very big field, and I'm fortunate to have two of the world's experts with me today, so that rather than my saying what they told me, they can tell you what they told me. So we'll start with Professor Amanda Lynch, and she's in the Department of Earth, Environmental, and Planetary Sciences here in Brown, but I'll let her introduce herself.
So I'm Amanda Lynch. I'm Lindemann Professor of Environment and Society, as well as Earth, Environmental and Planetary Sciences. It's a ridiculous title. I'm a climate scientist primarily, but I also consider how humans interact with our understanding of climate sciences and how we use climate information in making policy. I'm also chair of the research board at the World Meteorological Organization.
Great. And Baylor?
I'm Baylor Fox-Kemper. I'm a professor of Earth, Environmental, and Planetary Sciences. I'm an oceanographer and climate modeler. I mainly work on the physics of the ocean and how to improve the representation of those physical processes in climate models. And I was a coordinating lead author on the Ocean Cryosphere and Sea Level Change chapter of the recent IPCC 6th Assessment Report that came out this past August.
Great. And so we really do have two of the world's experts here, and this is a really complicated topic. It has a lot of differential equations and math underneath the hood, and we have two people who really understand sort of what's underneath the hood and how to talk about it at a high level. And we're just going to start, and I guess I'll throw this out to Amanda to start, but Baylor, feel free to jump in. I think it's hard for people to understand what a climate model actually is. Like, we talk about climate models, we talk about models, and within the scientific community, the idea of a model is well understood, but I think it's less well understood in the general public. So I'd like to start with, just at the very high level, what is a climate model and what do we use them for?
So climate models grew out of actually weather forecasting. So that's where this whole kind of journey towards creating models that could simulate the climate as it is now and project it into the future came originally out of our need for weather forecasts so that we could fly aircraft and send ships out to sea safely and things like that. And all of these models have the same kind of fundamental underpinning, the kind of the engine under the hood. And that is a set of physical equations that came from Newton. Basically, force is mass times acceleration is kind of the basic idea, but it's expressed as fluids moving around. So the atmosphere is a fluid, the ocean is a fluid, and these are all moving around the planet and redistributing the energy that's coming in from the sun. And so what we're trying to do is solve those equations, but because we're solving them in a computer, because you can't solve them on a piece of paper, they're too complicated, the computer is discrete, it can only deal in bits. And so you have to take the entire planet and break it up into little blocks of stuff, and you solve the equation for each block. And we call those the grids. And so for the grid in the atmosphere, the grid on the ocean, on the land surface, in the ice, we're solving those equations and other equations that go along with it. So not just the force equals mass times acceleration, but we're also solving equations associated with transformations of heat energy or movement of salt in the ocean and those kinds of things. So we're solving all of those equations. We solve them every few minutes and push that forward in time. And as we push that forward in time, if we're doing that just for 3 days, we get a weather forecast. If we're doing that forward in 50 years, we're thinking about a climate projection. And there are good reasons why those are very different things. That one is a prediction that we feel reasonably confident about these days, But when we go further out in time, we're starting to think about alternative futures, possibilities. And so there are, what we can know is different on different timescales, but it's exactly the same engine under the hood.
So I know one question that comes up for me a lot when I'm talking to people about this is, we can't predict the weather 2 weeks out. Why can we predict the climate 50 years into the future?
Because we're not predicting the climate 50 years into the future.
Okay.
Well, that's the kind of the fundamental difference. That with the weather, what we're doing is what we call an initial value problem. So we know where we're starting, and we're going to step forward in time, and then the small errors that we're starting with in knowing where we're starting, because we can't observe everything everywhere all the time, there are always going to be small errors in that starting point. And so as we move forward, those errors will grow. Even if the model was absolutely perfect and we knew everything about everything, the errors would grow. And that's what gives us the limits to the prediction of weather, which at the moment we've managed to push out to 10 days really well. So that's what's called an initial value problem. Beyond that point, the errors associated with our imperfect knowledge of the starting point are so large that we're really decoupling from where we started, and we start thinking about a boundary value problem, where what we're thinking about is what is a physical state that's consistent with everything we know about what's coming into this system. And so that boundary value problem depends entirely on what are the forces acting on that climate system in that future state. And again, our knowledge is imperfect, not just on how the system works, but also what's coming into the system, and even what are we going to do as we go forward. What are our emissions going to be? Where are we going to build cities? Where are we going to clear forests? All of those. There are so many things. A volcano might erupt tomorrow. That is going to totally change everything. So there are a lot of imperfections about what we can know about what's coming in at the sides. And so when we're thinking about climate, we are thinking about kind of alternative futures that are consistent with the forcing, and that's why we call it projection rather than prediction. I don't know if Baylor, you probably have a.
I was going to say,
can be more
so that's
precise.
a great explanation. I think, in my mind, the difference between that initial value problem and the boundary value problem is really the difference between weather and climate. Weather is an initial value problem. We predict for some short time, as long as we can, but it eventually runs out. This is related to the butterfly flapping its wings and changing the weather a few weeks out. So there is a fundamental limit to how far that goes that has to do with chaos, and fluid dynamics is inherently chaotic. So the fluid dynamics of the atmosphere and ocean is a chaotic process. But when we go beyond that, we start to get the influences from the boundaries, and that changes the system we use. So yes, there's still a weather model at the center that's being run, but we start doing things like running an ensemble of weather models to experience not just one particular weather future, but an ensemble of possibilities. And the climate is really the bounding of that ensemble. Once we get to those longer timescales, not only do human impacts come in, but things like the ocean, the cryosphere, that is the frozen parts of the Earth, the ice sheets, glaciers, their changes start to come into play when we get out towards decades, towards centuries, towards millennia, and increasingly so, where the weather is predictable on a short time scale, then the ocean is predictable on a somewhat longer time scale, up to perhaps a few years, which is where we have predictions of El Nino. And then the cryosphere and the deep ocean are predictable out to maybe centuries or millennia. And in those cases, the weather is acting like random noise around them. So it's the connections between these systems, between the atmosphere, the ocean, the biosphere, the pedosphere, the incoming radiation from the sun, and the release of energy back to space, where these boundary value problems really get realized through all of the spheres interacting on the Earth.
So let me give a concrete, simple example, and you can tell me if it's good or bad. So I often, when I try and explain this, I say, we might not know what a particular December day looks like in the future, or a particular July day looks like in the future, but we're pretty sure that the July day will be warmer than the December day. And that's sort of the difference between being able to predict the weather and knowing that what really is changing between December and July is something about the Earth's orbit, which is very predictable. And so on average, like, that makes sense. Does that sort of sum up this boundary versus initial thing that you were both talking about?
Yeah, it does. And so you can imagine how difficult it is to detect climate change in the face of this weather variability that's on top of it. So over decades, over centuries, we might see a slow transition and say the December weather getting warmer versus the summertime weather or versus its past historical values. And so that's difficult to measure, and no particular December will tip the balance. But as those statistics accumulate year after year after year, we can start to see these longer term trends, which is describing that ensemble of possibilities as they change. And so it's not only the mean temperature that we're interested in, we're also interested in the variability of the extremes, whether there were extra snowstorms or snow is turning into rain in December, or are we getting more drought conditions in the summertime. Those kind of pieces link together to give us what we understand as climate change, which is a whole set of different statistical behaviors about the weather that we would like to project into the future.
And I think also that, your example about the seasons is a really nice illustration of the idea that weather is this changing day to day. Climate is not a single number. It is cold winters and warm summers. It's cycles, but they're slower cycles, and that's what Baylor was talking about in terms of this idea of variability, that there are natural variations on those longer timescales, and it might be the El Nino Southern Oscillation, or it might be the Arctic Oscillation, or seasons, and all of those variations. And we know there are a lot of these, and a lot of them in the atmosphere. We call them oscillations. That it's the statistics of the variation that we often care about, as opposed to the mean temperature. And so we care in climate about the cold winters and the warm summers and the way that variation happens, and all of the other oscillations. They're all telling us about this whole state that's called climate.
But of course, the natural variations do not explain the recent behavior. The last century and a half is unprecedented in many thousands of years to maybe hundreds of thousands or millions of years, depending on which aspect of the climate system you're talking about.
Yeah, and I want to come back to that point for sure. And we have talked a little bit in previous modules about sort of shifting the mean and what that does to the extremes. And that's obviously a key point. No one cares if it's 80 degrees or 81 degrees on an average day. They care how many days over 100 degrees it is every summer, right? So that's something we're definitely going to come back to. I want to just talk a little bit more about the way that models and data interact before we move forward to my next question, because my understanding is that these models are refined continuously to include more and more things as we learn more and more things. And I think if people are not sort of familiar with the mathematical and statistical approaches that are under the hood, it can sort of sound to the average person like you could tweak these models to get a result that you wanted to get, or to, how do you know that you're not tweaking the model? So I just want to, you gave me a really good example once about the physics of ice. I don't know, do you remember that example? Can you tell me a little bit?
Sure. So this was based actually on a big observational program that occurred where we were measuring the physical properties of sea ice and wanting to understand how they were working in the atmosphere. And one of the things that we understood, being able to spend, this was 13 months on the ice, observing it in detail, is that ice that's on the ocean is really messy. It's not just that it's broken up and it moves around. That's a big problem, that the ice is moving all the time. But it's full of algae, it's full of soot, it's full of water pockets and bubbles, and so it's the way the ice interacts with the sunlight that's hitting it and then reflecting a lot of it is not a very clean, easy kind of process. And so based on the observations we made, we were able to come up with a much more nuanced description of how sunlight interacts with the sea ice, which is to do with what we call the albedo, which is the fraction of sunlight that's reflected back. And the problem was that when we put that in a climate model, all the ice went away. It melted everything. So even though we understood that what we were doing was physically appropriate, observationally grounded, it doesn't mean it's going to work well in a climate model, because a climate model is full of hundreds and thousands of interactions. There are so many degrees of freedom. And so the idea that you could somehow tune it to behave the way you wanted it to, it's just not possible. I wish we could, wouldn't that be great? But in fact, it's very, very complex. And so, so when you do something like that, where you do the right thing and get the wrong answer, that's telling you there's something else wrong in the model that we have to fix. So there are two ways you can deal with that. You can go back to your old bad way of doing things, or you can look for what you need to fix. And what we typically do in science is look for the next thing to fix. And then again, coming back to weather, weather every day gives us a kick in the pants of what we got wrong. And so it's one of the gifts to our field, I think, is that we do have a lot of observations, never enough, but we do have a lot of observations to continually check our understanding and say, are we getting this right? Where it gets harder and harder is when you go into the longer timescales that, for instance, the Baylor deals with in the ocean. It gets harder to get the kind of observations that you need. But nevertheless, they're always telling us, you got that part right, but you're getting this part wrong, perhaps in response to getting that part right.
Spoken like an atmospheric scientist, that you have so much data. I'm sure the oceans don't have quite as many observations, but I'm curious what you...
It's been changing, actually. So that was the case 20 years ago, but now we have a robot fleet of drifters that's continually profiling the oceans, and that allows us to track. Actually, the easiest way to track the changes in the Earth's energy is to measure the ocean temperature. And so we now have this robotic fleet that's patrolling the whole world. There are about 4,000 of them, and that's really changed our view, but we only have this for about 15 years. When you go back before that, we have measurements that depend on where the ships happen to be at the time, and it gets very complicated to try and match those statistically together. So when we think about evaluating models with observations, there's a lot of very sophisticated statistics, which has to do with the historical sampling pattern that we had available at the time. We still can say something. We can reject some models as being, wrong, but there are many models that are quite different, that are consistent with the past observations, because the past observations were limited. But satellites, autonomous fleets, remote sensing broadly has really increased the data volume. So now, about every month, we collect more in situ, in the water, observations of the ocean than we collected in the whole history of oceanography till about 1990.
Wow.
So,
I didn't know that.
Yeah.
That's cool. Okay, so that was awesome. Thank you both for explaining that. That's a really, really helpful, I think, and will be helpful for the class. I want to move now. So, we have an understanding now of how climate models work and what they can do. But I want to move now to sort of the second question that I really wanted to focus in on, and that is how we use these models specifically to attribute the warming and climate changes that we're observing now to human activity, as opposed to natural variation as the alternate hypothesis. And so I'm hoping that you both can sort of walk us through that process, and I guess I'll start with you this time, Baylor.
Sure. So I like to say that the climate activists like to say there is no planet B. But exactly what we need for this is a planet B. We need a control experiment without the effects of human activities. You can't do that in the real world. We've only got one planet Earth, and it obviously has human activities going on it, at least in the meantime. And then, anyway, in the synthetic world, within the world of climate modeling, it's quite easy to turn off the human activities and see what the differences are. And so when you do that, you can make an ensemble of all of the models from all the modeling centers around the world that don't include humans versus an ensemble of all the models around the world that do include humans. Both of them include all the natural forcing, volcanoes, solar cycles, orbital variability in the Earth's orbit, all that stuff can be included in both, but you leave the humans out of one. And when you do that, you find out that sometime between the 1970s and 1980s, in most variables, those two ensembles separate. So they're clearly distinct. That the temperature, continent by continent, or for the whole globe, is systematically different when you include human activities. But that's not enough to say that the changes we've seen are actually explained by that. You also then need to overlay the observations and show that the observations are only consistent with the models that include human activities. So the attribution has two steps. One is to identify whether there is a significant difference between with and without humans, and then secondarily to ask whether the observations can help you pick among those two piles. And for most large-scale climate variables, global precipitation measures, global temperature measures, continental scale, it is quite clear that there is a systematic difference between what's observed and what would be modeled without human activities.
So can I just, maybe for either one of you who wants to jump in on this, I want to just talk a little bit about how you actually remove human activities. So what you mean by that is we have an inventory of how much fossil fuel has been burnt and CO2 that's been put up to into the air because of that, or methane or whatever, and you just tell the model that didn't happen. Mm-hmm. And then for deforestation, for example, which is a carbon flux, you say not only were those forests not cut down, but also those forests weren't cut down, and therefore the carbon wasn't emitted to the atmosphere from burning them, and the color didn't change because they're still green as opposed to brown farm fields or whatever. Or how do you take people out?
The different forcings are specified in different kinds of ways. So let's leave the land use aside for a minute. So
okay.
The easy one is to say, oh, this is how much CO2 was emitted from fossil fuel burning. This is how much methane probably escaped. This is how many aerosols were produced. Those change the clouds. This is how many CFCs were produced. We actually know CFCs all the way back to their invention. And so you can put those pieces into the system. They very quickly homogenize in the atmosphere, and they have radiative impacts on change the clouds, they change the sun coming in, they change the long wave radiation going back out, and then they also get absorbed into the ocean. And we can then compare the ocean layers as they slowly take up those pieces versus observations to make sure that the water that's tracking those changes over decades to centuries gives us a consistent picture as well. So we get kind of consistent things to check in the models when we add that forcing, and we add that forcing to change the system. Land use is a little more complicated because land use changes whether humans are doing it or not. You know, sometimes trees die, sometimes trees catch on fire. Different modeling systems represent that natural variability at different levels of complexity. And so there's a diversity of opinions on how to do that. And that diversity is part of what we think about when we think about the many modeling centers around the world. We don't really know the right answer. We have a diversity of opinions, and so we make sure to preserve a diversity of models so that we have that diversity of opinions represented in the diversity of results that we include in those ensembles.
Yeah, and that's actually really a power of the approach, that by using many different models and different perspectives on how every element in the system works, we're really trying to kind of put an envelope around the possibilities. The other thing that we can do, apart from detecting that difference, what Baylor's describing is called the detection and attribution problem. So where you're detecting a difference between the two possible climate regimes, and you're attributing that to the particular greenhouse gases that you're adding and the land use change and things like that. But there are other things that we can do as well. So we know that the way the climate responds to the radiative forcing that you get, the heating that you get from, say, carbon dioxide, looks different in the system from the kind of heating that you get from, say, solar variations. And because we know that that fingerprint of change is different, we can look at those fingerprints. So it isn't just saying they're different and our observations look like this one, but it's also that they're different in exactly this way. And this way we know that the physics tells us that that's associated with human activity.
So would one example of that be, for example, stratospheric cooling?
Right.
Because you've put this CO2 blanket sort of down close to the Earth, and therefore not as much heat is making it up into the upper atmosphere,
Right.
which is not what would happen if sunlight was the warming
Yes.
agent.
Exactly.
Okay.
And you also, some people get very concerned about all detection and attribution being associated with models. Like, that's important, that's what we're talking about today. But there are also non-model based clues as to what's going on. Isotopic variation among the molecules in the Earth system is one great way to think about that. When we say that the CO2 in the atmosphere is changing due to the emissions from fossil fuels, there is both a consistency within a climate model simulating that, but also ways that you can go and measure the particular characteristics, isotopic and chemical characteristics of those tracers in the Earth system. So some of the evidence we have comes outside of the modeling, as when we think about, are humans doing enough, burning enough fossil fuels to make a difference? We can measure that directly as well as simulating it through models.
So I want to talk a little bit about sort of how we assess whether these models are right or if they're wrong, and if they're wrong in what way. I mean, we've talked about before this idea that all models are wrong and some models are useful. These models have to be useful for our understanding of the climate and what the climate's going to become under different scenarios of what we do. So how do we think about sort of making sure they're right?
So models have, one of the fascinating things about the climate system is that everything's hooked to everything. So models have problems in lots of different ways when we compare them to observations. When they're systematically wrong in a particular place, like always too hot or always too cold, we call that a model bias, or it's a model error, but of a particular type, where it's offset in one direction or the other. So the Southern Ocean sea surface temperature is something that's quite hard to simulate. Most models have a bias in their Southern Ocean sea surface temperature. If it does, then you say, well, what are the processes represented in the model, and how do they compare to the processes of the real Earth that also govern the temperature in that place? And so you might think about ocean mixing, or you might think about low-level clouds in the Southern Ocean, or you might think about the healing of the ozone hole and how that's represented. All of those things come into play in setting the Southern Ocean sea surface temperature. So that's model bias. We have already talked about the initial value problem versus the boundary value problem. Because you don't know what the weather's going to be on any given day that the model's simulating, you have to average over all the weather conditions and all the El Nino conditions. So you have an intrinsic uncertainty that's due to that internal variability. Then you also have a scenario uncertainty, which is, what are humans going to do? Are we going to do exactly what you expect, or are we going to do something different? And so the typical way that that's managed in climate modeling is to take different scenarios. What if we burn an awful lot of fossil fuels? Or what if we transition away from fossil fuels very quickly? Or what if we extract a lot of fossil fuels out of the atmosphere? Or what if we switch to methane but get rid of gasoline? Those kind of scenarios about a future possibility give us information that we can use to simulate that particular scenario. But as you get farther out toward the end of the century, the scenario uncertainty tends to dominate the overall uncertainty of the models. So it's not this model bias or model uncertainty. It's not the internal variability that dominates after a few decades out. It's really what humans are going to do that dominates the uncertainty.
And this comes back to your point about, all models are wrong and some models are useful. Thinking about what constitutes useful information. And that useful information is really different on different timescales. So if you're making decisions about, for example, intergovernmental negotiations on emissions controls that we have in the Conference of the Parties that we just had in Glasgow, that kind of information relies very much on these longer timescale questions about scenarios. And so the uncertainty about which scenario you're on is actually useful, because then you can start to think about, well, what if we chose this path, or what if we chose that path? What if we delay our emissions controls? What's the influence of a delay of 10 years or 20 years or 30 years if we end up at the same place? You know, so those kinds of decisions are that not only is the scenario uncertainty useful, but the fact that scenario uncertainty dominates at those timescales is also useful. When we're thinking about other kinds of decisions, for instance, investments in infrastructure, how you should do your planning and zoning of your coastal town, what size dam you're going to build in order to have enough water for this agricultural community. Those kinds of decisions are thinking more about decadal, maybe 2-decade timescales. And so at those timescales, the scenario uncertainty doesn't matter at all. And what you're really worried about then is model bias and model variability, and thinking about those things and how they're going to influence your design parameters. So different types of uncertainty matter for different decisions.
And things like sea level, the slow-moving parts of the system, really have a long committed level that's already built in because of our past emissions. So there's nothing we can do about sea level in 2050. It's already locked in where it's going. It has very little sensitivity to present emissions or emissions between now and 2050. The system's still catching up to what we already did. There's one other kind of climate model potential error, which is extremely hard to diagnose and extremely hard to chase out of the system, which are things that we've never observed to occur. So we're talking about unprecedented change versus paleohistory. There is the possibility, and some of these we are quite sure exist, of tipping points or abrupt changes in the system that lie sometime in the future. So if we have a tipping point and the Amazon forest dies back, or we have a tipping point and Antarctica starts to melt faster than we expect, those are things that we can't check against observations because they've never been observed to occur during human history. And so we can say they are physically or biologically plausible. We can try and estimate a safe threshold below which we don't think they are likely to occur. But the estimation of what happens after they're tipped or where that threshold lies is extremely difficult, because we can't, if observations, modeling, and theory are our three, the legs of our pedestal of understanding, if we don't have observations, we're standing on something quite tenuous to make those conclusions.
Yeah, it's funny, I also have sort of a standing analogy for this problem, which is that we're dancing blindfolded near a cliff. And so you don't know where the edge of the cliff is, but if you know that you're blindfolded and you know the cliff exists, you might want to be a little bit careful about exactly where you put your feet.
Yeah.
So yeah, that's a good explanation. And I think one of the things that I want to come back to something you raised, Amanda. You were talking about sort of difference between the models in the short term doesn't really, a difference in scenarios in the short term doesn't really matter because there's a bunch of uncertainty between the models. So just as a point of clarification, it's sort of this mystical council of models out there. How many models are there? How many models are there, and are they really independent? Like, are we really talking about independent models that are coming up with the same answer or a different answer? Or are we talking about one? Are we talking about 10? Are we talking about 100?
So yeah, I mean, you can correct my numbers if I'm wrong, but my sense is, looking at it from the World Meteorological Organization level, is that there are around 50 centers running about 100 models. And most of those centers, not all of them, run those models multiple times. in this ensemble mode that Baylor was talking about. So they'll start them off with slightly different conditions, and they'll vary them in different ways so that they can explore, you know, how variable that model is, how sticky its kind of core climate that it simulates is. So there are a lot of them. They are not all independent, and this is, you know, frankly, one of the issues that we face in organising ourselves through the Intergovernmental Panel's process of assessment reports, is that modelling centres want to contribute their models to this process. It's an incredibly valuable process. It feeds into negotiations amongst the Conference of the Parties to the UN Framework Convention. So you want to be part of that. The problem is then that you will not take risks with your model formulation. You won't try some crazy new theory if it's possible that test will mean that your model's not ready for the next assessment report. And so what that whole process has tended to do is to lead to a certain amount, not a lot, but a certain amount of model convergence, where people are converging on what everyone kind of agrees is more or less the right answer, and some of the kind of crazier ideas out there that might actually turn out to be right, we're kind of not testing them. So that is an issue with the infrastructure. I think that we don't want the perfect to be the enemy of the good here. In total, this kind of global effort of modelling development is a really important thing. A lot of it's volunteer, and so that leads to, I think, really important and useful information for underpinning decisions. But there is no doubt that there is some model convergence in that process, and we wouldn't say that every model is independent. There are a couple out there that are like made out of whole cloth, so to speak, but most of them they bolt on bits from each other's models all the time.
And they all go back to Newton.
And they all go back to Newton.
But we're pretty comfortable with Newton.
We're pretty comfortable with Newton.
At least as long as we're traveling slowly enough, right? You both have mentioned the IPCC. I know you're an author on the most recent report, but the class actually hasn't talked about that process. So since both of you are here, it would be great to just get a quick summary of sort of what is the IPCC and what are these reports, and how do they come about, and that would just be helpful for the students to sort of know that. We all see graphs from the IPCC all the time, but I think most people don't really know what it is. So I don't know who wants to jump up.
Well, maybe I could talk a little bit about the history, and then you can talk about how it works now.
Yeah. Great.
So what happened in the 80s, understanding about human influences on the climate system was really gathering momentum. People were really starting to see responses, and this comes from, you know, groundbreaking work from people like Suki Manabe in the 70s, really starting to hone in on, this human influence is not just possible, as had been postulated for 100 years, but significant. And not only that, we're going to be able to detect this probably, and the prediction in the 80s that we'd be able to see it by about the year 2000, which turned out to be more or less right. And so what happened then was that there were a series of climate conferences amongst scientists who started to not just talk about the science of climate change, but actually started to call for emissions controls, quite significant emissions controls, talking about limiting emissions, cutting them by 20% immediately, those kinds of things. And this group, a group coalesced around this. They were called the Advisory Group on Greenhouse Gases. That made a lot of people uncomfortable in government. And so the idea was, particularly in the US State Department and amongst number of other governments, that the initiative had to be taken back from the scientists and put back in government. And so through that process, there was a request made to form the Intergovernmental Panel on Climate Change. And so that was recommended to the World Meteorological Organization and the United Nations Environment Program in the late 80s. They agreed to do it and formed the IPCC. And then the IPCC then started the process of climate assessments that continue to this day. The first assessment was geared towards providing information to the Rio summit. From the Rio summit, we got the United Nations Framework Convention on Climate Change. So the IPCC, even though it exists more or less to serve as the information factory for the Framework Convention, it actually predates that convention because of this kind of initiative that was originally taken by climate scientists. And since that time, in that first assessment report, which was in 1991, there's been a new assessment of the current state of our understanding of the system every 4 or 5 years. Yeah, it varies. And there are a lot of interim reports that are updating specific things that are needed for policy decisions. And so then what happens is every year there is, in the fall, there is what's called a conference of the parties where there are negotiations on what we should do about this information. In the intervening 6 months, every spring, there's a kind of a technical meeting that typically happens in Bonn where there's a discussion of, what science and technology information is going to be needed for that. And so there are meetings every 6 months, of which the Conference of the Parties is the big public one, and what they call the Subster, which I attend, is the kind of more private one. And that's continued lockstep since 1992.
So before we get to Baylor and what the process is like in this last assessment report, I want to ask a very high-level question. Does the 1991 report say anything that is dramatically different from the most recent report?
Some things it does, actually, because we couldn't detect. We couldn't detect yet. So there's no attribution. There's really very little minimal detection. And many of the things that say you came in, so the IPCC has this sophisticated confidence level process where things come in at low confidence or medium confidence or high confidence or very high confidence, or they're just a fact. And in that report, when you go back, it even precedes that language. But they say, the human impacts, make sense to us, but we haven't detected them. Whereas now there is a change in the climate system. That's a fact. It's not even with a confidence level anymore. And there's a human impact. Human activities are leading to that change, also taken as a fact. It's not something that has a confidence level anymore. So it's not that the kind of statements have changed very much, but the confidence in them has changed dramatically.
Yeah. Okay. So tell us a little bit about your involvement and just what the process is like. I mean, I think people, okay, but we only have two and a half more weeks.
Exactly. Yeah.
But really what I want to know is, I think that people have a bit of a misconception that the IPCC is doing science as opposed to synthesizing or recommending policy. So can you tell us a little bit about sort of what is actually the purpose of these reports and how they come about? And
So from the framing that Amanda just provided, I mean, the IPCC specifically does not recommend policy. That's less to the COP. The IPCC just provides scientific information. So it's not, you should do A. It's, if you do A, then you will get B. That's all that's provided from the IPCC. And there are 3 different working groups. The one that I'm part of is the physical science basis, which is, emit this amount of greenhouse gases. This is how much the Earth will warm. The second one is impacts and adaptation. So it's a more localized perspective, and it's like, what technology do we have to adapt to these changes, build climate resilience? And then the third one is about mitigation, which is reducing our emissions in the first place. What technologies, how much do they cost, all of those pieces. None of those recommend choices. They give kind of a menu of options, and then from that menu, the COP takes off. But the scientists who are part of the IPCC has an office, and they kind of just coordinate all the activities and all the meetings and all the reports and all the publication of those reports and the proofreading and the type edit setting and all of that. But most of the people involved in the IPCC are volunteer scientists like myself. from all over the world. This report had 230-something lead authors, about 25 coordinating lead authors like me, and probably 1,000 total authors, including contributing authors and chapter scientists who are early career scientists who are recruited by the IPCC to help in production of the reports. And they're from all over the world, most, dozens and dozens of countries, not all of the countries that are involved in the UN, but a large fraction of them. They do that both because it's a good opportunity for the scientists to come together and get to know each other, but also because the scientists are then representatives for that science when they go home. It's easier for me to speak to people in Rhode Island about climate change than it would be for somebody from Europe to come to Rhode Island. That would be an interesting thing to watch. Anyway, we're not doing new science, we are assessing existing science. So many of us are involved in the production, all of us are involved in the production of climate science, but we do that in our day job. In this volunteer activity, we're reading reports and we're discussing and trying to come to consensus about what those reports imply for the present state of understanding. And so the key thing is you want multiple lines of evidence. So you want not one paper. It might be the best paper ever, but that doesn't get weighted very heavily by the IPCC. You want multiple papers using multiple techniques that have consistent agreement in the results and implications to make those results be the ones that get high confidence. Otherwise, a new result that's maybe very important, has big impact, might get into the report, but it would come in with low confidence. Or if there are lots and lots of work, but they all disagree because they haven't figured out what the real underlying truth or how to measure it is, that also comes in at low or medium confidence. So the confidence is deciding what goes in the report is a big part of the work. Deciding what confidence level to give it is a huge part of the work. And then figuring out how to keep it limited in duration is also limited in scope. So this report, we assessed over 14,000 scientific papers. There's a review process. We had 3 drafts of the report that were reviewed by experts. That includes climate skeptics, that includes contrarians. Anybody who thinks they're an expert can be an expert reviewer. That's the standard. So we had over 78,000 review comments. So our chapter reviewed 1,500 papers and had over 10,000 review comments. And every single one of those, someone in our chapter replied to, someone else checked to make sure their reply made sense. And they are all public. So all of it is transparent. What we did with every comment to all of those 78,000 people, or it's not quite 78,000 people, but 78,000 comments are all replied to. So it's this exhaustive thing. So you wouldn't be surprised to find that it's a 4,000-page book. But then the next work is to summarize, because we're trying to communicate to policymakers. So there's something called the technical summary, which combines all of the different chapters from the 4,000 pages and gets just the real highlights for a technical audience, other scientists, but across all aspects of the Earth system. And then the policymaker summary is a 10-page document that has just the things that are of the highest confidence and most policy relevance singled out in the plainest language we can manage while still remaining scientifically accurate.
Which is what you, class, will be reading.
Right.
So not the 4,000 pages, just to be
You
clear.
can read the 4,000 pages too. It's all online. It's there for your browsing. But yes, stick to the policymaker summary to begin with.
So how many hours do you think you personally spent as a coordinating lead author?
I estimated somewhere between 10 and 20 hours a week for 4 years. So it was pretty much 25 to 50% of my job, and that was volunteer time. So Brown essentially subsidized the IPCC by paying me during that window.
Wow. Yeah. Thank you.
Yeah.
I had a couple of thoughts about sort of the assessment, and it made me think of a jury trial, right? And it seems like the stakes are really high. And so, for example, in a criminal trial in the United States, you have to prove beyond a reasonable doubt. And in a civil trial, which is presumably lower stakes, you have to have a preponderance of evidence. And these kind of evidentiary rules are, and so is it fair to say that, you know, when the IPCC says something like it's a fact or we have very high confidence, what you're sort of saying in legal terms is beyond a reasonable doubt that this is the case?
Yeah, so there's a whole language for that. Not surprisingly, there's something called likely, which is 66% likelihood, and then there's very likely, which is 90%. You know, so they have similar language that allows us to convert probabilities into language.
Yep.
And it's highly formalized, like the preponderance versus beyond a reasonable doubt. The ones that are taken as a stated fact is beyond a reasonable doubt.
Right.
It's really something that, though it may not be in children's textbooks yet because it's cutting edge science, it is a fact at that level. We would place it alongside, you know, Newton's laws. This is a discovery about how the way our world works.
Right. Okay. Great. So, unless you want to add something to the IPCC story, and thank you both for that because it's a very opaque process to the outside world. I want to talk a little bit about the use of models for the future scenarios, and you've already touched on. You both kind of talked about this, but you know, the IPCC does consider, you know, if you did this, what would happen? If you did that, what would happen? And I want to talk kind of about two things, and either one of you can jump in. One of them is sort of how do we pick what those scenarios look like? Like what are those scenarios? Because often the IPCC, for all its plain language, labels them things like RCP 8.5.
SSP 585.
Yes.
Sorry, yes, which is wildly transparent, and everybody knows what that means. So one, just like, let's talk about these scenarios and sort of which scenario we're on. And you know, people have heard a lot about Paris or limiting to 1.5 degrees or limiting to 2 degrees or whatever. So that's one thing, like how do we choose them and what are they? And the second thing is, what do they mean for people who are going to live through 2050, for people who are going to live through 2070? You know, students who are taking the class today who are 18 or 20 years old, they're going to be around for a lot of these, a big portion of this scenario. So what does it show us in terms of what our world will look like given a change in course or no change in course? So who wants to start with that easy one?
Well, I can talk a little bit about how the scenarios are built. So scenario building is another part of the expert process that goes into the whole IPCC kind of rolling series of assessments where experts come together and they talk about different ideas of how the world will evolve economically and socially and industrially. And so those ideas include things like, you know, will we get more globalization or will we actually get more kind of parochialism or regionalism? You know, will we pursue a path of industrialization that uses more renewables or one that's more heavy on using hydrocarbons? So there'll be a series of postulates about different socio-economic pathways and some technological pathways, although we tend to avoid as much as possible in the scenario building a kind of a techno-utopian idea that somehow, you know, in 12 years' time, we're going to invent something that is going to solve all our problems.
Fusion for everyone.
Yeah, fusion, although I'm very excited about the
too.
latest fusion results from MIT. It's really exciting. But putting that aside, the desire is to kind of avoid, you know, that last minute, you know, Superman saves us from disaster type thing. And so then based on that, you can develop a sense of what emissions will be associated with that, and to a certain extent also the land use and land cover changes that are associated with that, although, as Baylor said, that it's always tricky, that part. And then based on the emissions, we then need to turn that into what concentrations of what constituents are going to be in the atmosphere, in the ocean, absorbed by the land surface. Most models these days calculate that part themselves. There are still some models that actually need to be handed the atmospheric oceanic concentration information directly, but most models now you've just got to give them the emissions and they work everything else out. And so then from there, you can start to run those different storylines of, you know, what the world will bring and what the consequences of that are in terms of how the Earth system responds. Did I leave anything out?
Yeah, no, that was great. I mean, so this couples together with the kinds of uncertainty we were talking about before. So this is the scenario uncertainty part. But even if you know the scenario precisely, and we all agree, you know, this is the scenario named blah, 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 models will still disagree in what the outcome in terms of the climate change is to go alongside that scenario. So there is, you know, different models will have different El Niños in different years. Different models will have biases in different places. And so there is still an uncertainty around the scenario uncertainty. But as we go into the far future, the scenario uncertainty tends to be the biggest.
And one of the terms that we use for this is model sensitivity. Mm-hmm. So some models are more sensitive than others. You give a model the same kick, and some models will go, and some models will go, ow, you know. So there will be that kind of real difference in sensitivity in the models and how big the response will be to the given kick that you give it.
And it's quite a difficult thing, the socio and economic aspect. So the part we didn't talk about the IPCC is the government approval at the end. All the governments come together and make sure that that policy for summary for policymakers is every single word of it has to be approved by all the governments. So one thing that they got particularly excited about was in the previous report, these were called RCPs, Representative Concentration Pathways, and that's a suitably vague term. In this report, they're called SSPs, Shared Socioeconomic Pathways, and they didn't like that socioeconomic was in there because they thought that that implied a hint of policy prescription. And so they didn't want socioeconomics to be part of this, although it obviously has to be part because we're trying to come up with a realistic range of plausible scenarios. So in many places in the report, the shared socioeconomic pathways was replaced with illustrative scenarios to be particularly clear that this was not meant to imply do this or do that, just to illustrate a range of possibilities.
Okay, so I think the last thing I want to touch on then is about the range of possibilities. So, you know, the world has warmed by about a degree or so since the start of the Industrial Revolution, a degree Celsius, that is. And in the news, we hear a lot about the potential to stay with only a total of warming of 1.5 degrees Celsius. And I think I myself am skeptical of that, absent Superman coming to save us, but perhaps we will get there. What does the path we're on now lead us to? Or is that even an answerable question, given the rapid change of technology, for example, the drop in price in renewables, and, you know, do we have any business as usual anymore? The IPCC used to say, you know, we're going to compare to business as usual. Does the IPCC still talk about business as usual?
No, specifically not, because that was a little too leading of a term, maybe. But among the RCPs, you can ask which is the closest to what we have done, because it actually started back in 2006, I think, was the forcing. Mm-hmm. And so we have 14 years to compare, 15 years to compare. The SSPs start more recently than that, and so there's not a whole lot of time. They haven't really spread out that much as of yet for us to pick one. But also, we have actually been seeing a lot of changes in policy and a lot of changes in renewable production. So we are shifting among the scenarios in a way that is hard to figure out exactly what pathway we're on. So it's easier to take the policy promises from the COP and project them into the future and see which is closest to which we're following. And in that sense, although it involves a lot of things that are just promises and not yet law or not yet built infrastructure, that is at least a hint as to where we're going and which scenario we're on. Fossil fuel companies use these scenarios to plan out what their prospective future is. So you could say that you should believe the scenario that they are behind because that's what they intend to do. So barring government intervention, barring carbon taxes and things like that, that might actually be the scenario that we're on, because that would be the effectively business as usual. But there's a lot of things, many of these involve like carbon capture from the atmosphere at levels that we presently don't know how to do, coming very soon. So technological breakthroughs could jump us from one scenario to the other by making that less expensive, or the opposite, technological failures could make us unable to stay on one, even though that's our intention, because we just can't get that technology together. So there's a lot of difficulty in figuring out what our trajectory is.
Yeah, and I think that while we're not seeing as much significant action as we would hope to get to 1.5 degrees, or even, I'm wondering about 2 degrees, while there is a lot of promises and not necessarily a lot of really substantial action across large enough economies to get us where we need to go. The way that I often think about this, and the way I discuss it with my students, is there is no point at which you give up and say there's no point doing anything. There is no point at which you say, right, let's not worry about any of these, building these scenarios anymore because it's all hopeless. Because every kilogram of carbon dioxide that we keep out of the system is a good kilogram, And so there is no point at which you give up. Now, the corollary of that is, of course, it can always get worse. But I think the better way to think about it is the hopeful way, which is that everything we do, every step we take is a step in the right direction.
And that reminds me of one point we haven't touched on yet that I think is really critical, is that what counts for the warming level we ultimately stabilize at is not the emissions in the future, it's the accumulated emissions. So how many tons of carbon have we emitted from the beginning of industrialization until we stop? That's what sets the warming level. So when we say net zero 2050, that's great, but how are we going to get there? Are we going to start this year reducing, or are we going to wait till 2050 and then try and do it all at once? Because the second is not nearly as effective as the first. It's the reason why a scenario is a helpful tool is because it tries to realize those transitions and convert it into the most useful relationships for forcing to response. And so it's easy to say, well, net zero at some indefinite phase in the future, but no plans today to do anything. That's an easy promise to make, but that actually means that we're still accumulating all those emissions. Some promises in the near term for a modest reduction, some promises in the long term for a long-term target need to go hand in hand. You should be very suspicious of one without the other, either way you go. Because it's easy to cut some emissions now, but there are some things that are going to be very costly to cut. And getting that all together is where this whole complicated negotiation at COP and elsewhere and state legislatures is going, right? As it's a difficult, complicated process that involves everyone. Every single person on the planet is involved in the emissions of carbon. Carbon dioxide is our #1 by mass product of human society. We're all engaged in this. Everyone needs to be part of the solution, and everyone needs to be part of a fair solution involving values and equity across all of our societies.
All right. Well, thank you both so much for giving me so much of your time. I'm super excited to learn from you both and for the students to learn from you. So thanks a lot. And I look forward to seeing you in the faculty meeting, I guess.
Yeah, right.
Thanks so much.